Okay, just wanted to look at, well, as the heading suggests, just some different types of induction problems that have appeared over the years. Now, keep in mind, this is HSC, so this is like endpoint. So don't panic with some of these. Oh, this was a beauty, actually. It looks horrible, but it's not too bad when you actually sit down and go through it. So they've given us a hint. We're going to use our tan alpha minus beta formula, tan minus tan on 1 plus tan tan. And we're going to show this wonderful expression, 1 plus tan n theta, tan n plus 1 theta. So all right, they've told me what I've got to start with. So my logic said when I was looking at this, I've got two angles. I'm going to use alpha and beta. When I look at the answer, there's two angles. Well, there's three angles. There's theta, n plus 1 theta, and n theta. So it seems logical to use n plus 1 theta for alpha and n theta for beta, because when you subtract them, you'll get the you'll get the theta, which is the other bit that's in the what we're trying to prove. So let's see what happens. There it is, substituted in. So as I say, n plus 1 theta minus n theta, there's the theta. So we've now got all the three angles that we're trying to get to in the answer. Now, have a look at the denominator, 1 plus tan, n plus 1. That, in fact, is the left-hand side of what we're trying to prove. So if I multiply that, but then, again, looking at what the cot, well, cot, of course, is the reciprocal of tan. So if I divide by the tan theta, and that, I think, well, I haven't changed it to cot theta. Let's change it to cot theta. That's what we were trying to prove. So it actually wasn't too bad. I mean, they gave us the hint of use the tan alpha minus beta. I suppose it was matching up which angle to use where, and then it dropped out. That, of course, wasn't the tricky part of the question. Just the examiner's comments they said about this one. Interestingly, it was not actually done well. Many presenting circular arguments, so they might have ended up with statements like, 0 equals 0 and that sort of thing. However, a number did successfully rearrange and easily saw which substitution to use. So, okay. It was only worth 1 mark. So the induction part. This is a little bit different. So tan theta, tan 2 theta, tan 2 theta, tan 3 theta. So it is a series type. The general term, tan n theta, tan n plus 1 theta. Okay, so let's approach it like a series type. Prove it for n equals 1. Now, I'm actually starting with the right-hand side here. So when we sub n equals 1 in, I've got negative 2 plus cot theta, tan 2 theta. Now, I don't really know what I'm going to do with that, so now let's go to the left-hand side. Left-hand side is tan theta, tan 2 theta. Okay, I've got tan 2 theta on both. I'm going to add 1 and subtract 1. What? Why do that? Well, you've got to be thinking, why did they ask me the first part of the question? And the first part of the question had the 1 plus tan theta, tan 2 theta. So if I create that, but then obviously I need the minus 1 to balance it out. So the 1 plus tan theta, tan 2 theta becomes cot theta, tan 2 theta minus tan theta. Expand that out. Cot times tan's another negative 1. So that gets me the negative 2 we've got over there. And so, excellent. We've shown they're the same thing. So it's quite a tricky just showing true for n equals 1. So hence the result is true, etc. Okay. Assume it's true for n equals k. Okay. And we're going to prove for k plus 1. So there's our expression we're going to try and prove. Again, it's a series type. So I'll rewrite it as sum to k plus the k plus 1th term. My sum to k is my assumption. So I can sub that in. Now, we're going to play with this. Have a look at what I've done. Again, I've used that tan from part I. And then we'll end up with cot theta outside of tan, k plus 2 theta, minus tan k plus 1 theta, but then minus 1 because the actual thing was 1 plus, if you remember. Now, expand that all out. The minus k plus 1, minus 1. So that gets me the minus k plus 2. That's I think we were looking for. Then I've got cot theta, cot theta, plus with the tan k plus 1 theta and a minus, so that will cancel. So I have minus k plus 2 plus cot theta tan k plus 2 theta. And that's what we were looking for. So hence it's true for k plus 1, it's true for k, etc., etc., etc. So, yeah, let's see how they went. Most attempted it. That implies some didn't. However, many only earned the mark for stating the inductive step.
What does that mean? Like just using induction?
Well, see, it probably would have been worth, I don't know, 3 marks maybe. And they've got to make sure it's possible to get 1 mark, 2 marks, 3 marks. And usually you find with a 3-mark question, the first mark's very easy to get. Now, perhaps because this was so difficult, they were going, whoa, we've really got to lower the bar for this 1 mark. And so this particular year, they said, well, all right, well, gosh, at least if they know the idea of induction, so we'll see if they've done that, we'll give them a mark, you know. Now, that's not to say they're going to do that every year. Yeah. That would be unusual, but possibly, as I say, because of the level of difficulty of the question, they might have done that. As I was saying, n equals 1 actually was particularly tricky. That's usually where you get your first mark, is, oh, well, if they show it true for n equals 1. But in this case, n equals 1 was so difficult, well, apparently, as they were not able, didn't even link in part I. Right? So you're sitting in a test, you think, well, why on earth did they ask me that part I? Why wasn't this just a separate question? There must be a reason. So, I'm going to use it somehow. And consequently, they couldn't go and prove the inductive step. All right, let's have a look at 2004. Again, this one's a little bit different because instead of adding the terms together, we're multiplying the terms together. But we can still use the same idea. So, the first case, there we go, is 3. That makes sense because have a look at the first term here. That fits in with the general term. So n equals 3, we get a third. The right-hand side, yep, that's a third as well. So good, that works. Hence true. We'll assume for k, and we want to prove for k plus 1. So there it is, that's what we're trying to prove. So I'll use the same idea, except we're doing multiply instead of adding. There's my assumption. Well, it's not a sum, it's a product of the k terms. So we have 2 on k plus 1, times 1 minus 2 on k plus 1. Well, it makes sense to make that second parentheses there 1 fraction. So k plus 1, top becomes, that's nice, that becomes k minus 1. Actually, gosh, that does drop out nicely, doesn't it? Because that becomes k minus 1, which just cancels with the k minus 1. And then, bingo, it drops out. So, it actually wasn't too hard. But what would have thrown people is it's multiplying rather than add. So those people that just rote learn, how to do things are thinking, oh no, I've got to add the next term and things like that. But remember, induction is an idea. So the idea is prove it true for the first case, then induce the solution by getting your assumption in there somehow. So hence the result's true, etc. Comments. Many submitted excellent responses. So they said, okay, a lot of people did pick up on the idea and were able to use the inductive process. Weaker ones that did not verify for n equals 3. So they probably tried n equals 1 because, gosh, we always do that for induction. First case n equals 1 and went, this is not working. Had an incorrect statement of the assumption or an incorrect use of the assumption. And obviously if your algebraic fraction skills and that, whilst it was very easy cancelling, if you screw up the factorising and what have you, it then becomes a little bit harder. That's what I was saying. Just rote learning that idea of sum to k plus term k plus 1. That's what led many to, basically get it wrong. Did it as a sum rather than a product. Okay.